Hello everyone. So, in today's class, first we will derive the energy equation in non-dimensional form, then we will solve the governing equation for flow over flat plate using similarity method. This solution is known as Blasius solution. Blasius first solved this equation using similarity method and derived the ordinary differential equation which you can solve using some numerical technique. So, first let us see what we derived the energy equation in dimensional form. So, if you see for laminar Newtonian fluid flow with constant properties, this is the energy equation we derived, right. So, this is the temporal term, this is the convective term, this is the diffusion term, and as it is constant properties. So, the thermal conductivity we can take it outside, and this is dP by dt plus mu into phi, where phi is the dissipation function. So, dissipation function in general is given in this form. If it is a incompressible flow, then obviously divergence of V is equal to 0. So, last term will become 0. Using this non-dimensional parameters, now you please convert this energy equation in non-dimensional form. So, what we will use? We will use some reference velocity u infinity and reference length L. Okay. So, these are some characteristic length L and characteristic velocity u infinity. For external flows, generally we take the free stream velocity as reference velocity, that is your u infinity, and for any geometry we find the characteristic length and that length we take as reference length L. So, you can see using this reference velocity we have non-dimensionalized the velocity u star as u by u infinity. Similarly, V star is equal to V by u infinity, W star is equal to W by u infinity. The temperature, non-dimensional temperature we have defined as T minus T infinity divided by TW minus T infinity, where TW is the wall temperature and T infinity is the free stream temperature. Similarly, the coordinate we have non-dimensionalized using the characteristic length L. So, x star is equal to x by L, y star is equal to y by L, z star is equal to z by L, and the pressure we have used P star is equal to P by rho infinity square, and the time T star is equal to T into u infinity by L. So, these are some non-dimensional parameters used to convert this dimensional form of the energy equation to non-dimensional form of the energy equation. So, as homework you just do it and finally you will get this equation. So, you can see we have written in non-dimensional form. So, this is the convective term. In diffusion term, this non-dimensional numbers comes 1 by Reynolds number into Prandtl number. In this term one new non-dimensional number comes, that is your Eckert number, and with the dissipation function you will get Eckert number by Reynolds number, and obviously you know how the dP star by dt star is defined. Okay. So, this is the material derivative. So, now let us define the non-dimensional numbers. So, this conversion from dimensional form to non-dimensional form using these non-dimensional parameters you can do as a homework, and now you can see the definition of these non-dimensional numbers which we encountered in the non-dimensional form of the energy equation. So, first non-dimensional number is Eckert number. So, what is Eckert number? Eckert number, if you see that it will be u infinity square by Cp into Tw minus T infinity. So, that means it is the temperature difference. So, you can see that in the numerator you have kinetic energy of the flow and in denominator you have boundary layer enthalpy difference. So, you can see Eckert number is the ratio of kinetic energy of the flow to the boundary layer enthalpy difference. Okay. And Prandtl number, you know Prandtl number is mu Cp by K, and Reynolds number is rho u infinity L by mu, where rho is the fluid density, u infinity is the reference velocity, L is the reference length, and mu is the dynamic viscosity of the fluid. So, these two non-dimensional numbers you are familiar with, but this is the new number Eckert number which we can write in this form. So, with some mathematical algebra you can write Eckert number is equal to gamma minus 1 into Mach number square divided by T w by T infinity minus 1. Okay. So, you know what is Mach number? Mach number is the ratio of fluid velocity to the local sound velocity. So, that means Mach number you can define as u infinity divided by a, where a is the local sound speed, and gamma which is the ratio of specific hits, okay, Cp by Cv. So, you can see in this equation that if Mach number is very low, then Eckert number also will become very low. So, here you can see whatever energy equation we have written in non-dimensional form. So, if Mach number is very low, then these last two terms you can neglect, because Eckert number will be very low. So, you can see these two terms in the energy equation you can neglect, and for laminar incompressible flow generally Mach number is very low, and for that you can drop these two terms and you can write the energy equation in this form. Okay. So, it is in non-dimensional form, and if you write in dimensional form the energy equation for incompressible fluid flow, then this will be your energy equation. Now, let us consider flow over flat plate. So, this is the simplest solution we can do for flow over flat plate, because your pressure gradient is 0. So, first let us write the governing equation. We have already derived the boundary layer equations for flow over flat plate. So, continuity equation So, what is continuity equation? Del u by del x plus del v by del y is equal to 0. So, while deriving the boundary layer equation for flow over flat plate, what are the assumptions we took? We have assumed that it is a steady flow, two dimensional flow, and incompressible Newtonian fluid flow. So, for that you can write the continuity equation like this, and momentum equation you can write u del u by del x plus v del u by del y is equal to nu del 2 u by del y square. So, this is the boundary layer equations, right. These are boundary layer equations. Okay. Now, you can see these equations are non-linear, because the momentum equation you can see these terms are non-linear. So, it is difficult to solve analytically. Blasius first time solved these equations using similarity method. So, when can you use similarity method? First you see the velocity distribution for flow over flat plate. So, if you see, this is the length of the plate L, x is the axial direction, y is measured from the flat plate, u infinity is the free stream velocity, and if you see at any location x 1, so this will be your velocity profile. So, velocity from 0 it will develop, and at the edge of the boundary layer. So, this is the edge of the boundary layer, it will become free stream velocity u infinity. Similarly, if you see at location x 2, so here also the velocity will vary, okay, velocity will vary u from 0 to u infinity, because u infinity is the free stream velocity. So, at the free stream velocity u infinity is constant for flow over flat plate. So, you can see in these two locations that velocity profile looks similar, except it is with a scaling factor. So, if you see at x 2 location, whatever velocity profile you can see, if you scale it down, it will be similar to the velocity profile at x 1 location. Okay. So, we can see that as this velocity profile looks like similar with a scaling factor, so we can use the similarity method to solve these governing equations. So, Blasius first observed that if these two independent variables x y, if you convert it into a single variable eta, where eta is function of x and y, then with the scaling factor all the velocity profile at different locations will fall in a same curve. So, here if you see that if you plot the velocity u by u infinity, okay, so u by u infinity, so you can see that u will be 0 at y is equal to 0 and at the edge of boundary layer you have u infinity, so it will become 1. And if you plot this velocity distribution with y by delta, okay, y by delta, delta is the boundary layer thickness. So, at any location delta is the distance from the flat plate to the edge of boundary layer where the velocity becomes close to free stream velocity u infinity. And at different location if you plot this u by infinity versus y by delta x, because delta will vary with x, so delta is function of x, then he observed that it will fall in the same curve. So, it will look like, okay. So, you can see this is the velocity 1, okay, and this will be also 1 because at y is equal to delta this will become 1. So, it will fall in the same curve at different location, okay, along the axial direction at different x location. If you plot the velocity in this curve u by infinity versus y by delta x, it will fall in the same curve. So, you can see that velocity profiles are similar. So, that is why we can use the similarity approach to solve these governing equations. Now, you can see that we have defined y by delta, delta is function of x. So, obviously, we can see that we can define one variable eta combining the two independent variables x and y such that it will become y into g x. So, combine the two independent variables, x and y into a single variable eta which is function of x and y, and postulate that u by u infinity depends on eta only. Okay. So, now this eta will be function of x and y. We do not know what is the function, but it will be function of y and x. So, we will write, because we can see from here that delta is function of x. So, it will be function of x, but that is unknown. So, let us define the similarity variable eta, as y into g. G is a function, we do not know what is the function. So, which is function of x. Okay. So, now what you can do? So, now you can see that these independent variables x and y we have combined into a single variable eta such that u by u infinity is function of eta only, okay. Some function, we do not know the function, but function of eta only. Now, we have the governing equations, we know u with some function of a. So, we will just substitute all these in these equations and we will derive the Blasius equation. So, we have seen that eta is equal to y into g, where g is function of x. So, we can write del eta by del x. Okay. So, y into dg by dx, right, because g is function of x only. So, you can write ordinary derivative, that means y into g prime. So, g prime represent the derivative of g with respect to x. Similarly, del eta by del y you can write as only g. Now, we know the velocity profile u as u infinity into f, okay, and we will see the derivative of u with respect to x and y. So, u is equal to u infinity, where u infinity is the free stream velocity into f, okay. F is function of eta only, okay. So, it is function of eta only, okay, and g is function of x only. So, first let us write del u by del x. U infinity is constant, so you can take it outside. So, you can write df by d eta, okay, and del eta by del x. So, del eta by del x you know y into g prime, and df by d eta you can write f prime. So, you can write u infinity del eta by del x is y into g prime and f prime. Similarly, you take the derivative of u with respect to y. So, del u by del y. So, it will be u infinity df by d eta into del eta by del y. So, del eta by del y is g. So, you can write u infinity into g into f prime. Okay. Now, take the derivative of del u by del y with respect to y. So, you can write del 2 u by del y square is equal to del of del y into del u by del y. So, what you can write del u by del y we know, right. So, we can write del of del eta into del u by del y into del eta by del y. Okay. So, this you can write. So, now you see this is the del u by del y. So, you write the derivative of it with respect to eta. So, u infinity is constant, g is function of x only. So, it will be f double prime, and del eta by del y is g. So, you can write u infinity g f double prime, and del eta by del y is g. Okay. So, you can write it as u infinity g square f double prime. Okay. So, del 2 u by del y square is u infinity g square f double prime. Now, let us substitute this in the momentum equation. Okay. So, from momentum equation, okay, you can write u del u by del x plus v del u by del y is equal to nu del 2 u by del y square. So, here you can see, here we have already found u del u by del x, del u by del y, del 2 u by del y square, but v is unknown. So, let us find v. So, v will be nu into del 2 u by del y square minus u into del u by del x divided by del u by del y. Okay. So, you can write v is equal to, so nu into del 2 u by del y square. So, we have already derived u infinity g square f double prime minus u is u infinity into f, right, and del u by del x we have derived as u infinity y g prime and f prime, and divided by del u by del y. So, this is your u infinity g into f prime. Okay. So, from here you can see that you can write v is equal to, okay. So, you see u infinity will cancel out, one g will get cancelled. So, you will get nu into g f double prime by f prime, and the second term 1 u infinity will get cancelled and f prime will get cancelled. So, you will get u infinity y f g prime by g. Okay. So, we have found the V. Now, if you see the continuity equation, so in the continuity equation we have del B by del y. So, let us find del B by del y from here. So, del B by del y we can write as del V by del eta into del eta by del y. Okay. So, now you see del B by del eta. Okay. Del B by del eta is from here you just find. Okay. So, nu into g. Okay. So, now you can write d of d eta into f double prime by f prime. Okay. So, this is your first term, and minus now del of del eta of this. So, it will be, so you can see, so there are two terms y and f. So, g is function of x only. So, you can write u infinity, okay, y g prime by g and f prime. Okay. So, we have taken the derivative of f minus, so u infinity f g prime by g into del y by del eta. Okay. And we have del eta by del y. So, what is del eta by del y? Del eta by del y is nothing but g, and here del eta by del y is there. Okay. In the denominator if you see, it will be del eta by del y and that will be also g. Okay. So, now you multiply g and write it. So, it will be nu g square d of d eta f double prime by f prime minus, so this g will get cancelled. So, it will be u infinity y g prime f prime minus, you can see this del eta by del y, one g will be there and one g will get cancelled here. So, you can write u infinity f g prime by g. Okay. So, this is your del b by del y. Okay. Now, let us use the continuity equation. So, you can write the continuity equation del u by del x plus del b by del y is equal to 0. Okay. So, this is the continuity equation. Now, we have already found del u by del x and also we have found del b by del y. So, you can see del u by del x, whatever we have found, del u by del x is u infinity y g prime f prime and del b by del y is this expression. So, let us put in the continuity equation. So, if you put it here, so del u by del x is u infinity y g prime f prime plus del b by del y nu g square d of d eta into f double prime by f prime minus u infinity y g prime f prime minus u infinity f g prime by g is equal to 0. Okay. So, if you can see that this term and this term is same, okay, with a minus sign. So, you can cancel it. And now you notice, you see g is function of x only and f is function of eta only. So, you rearrange such a way and separate the variables such that in the left hand side will be function of eta only and right hand side will be function of x only. So, if you write and rearrange, then you can write d of d eta f double prime by f prime, okay, and one f is there here. So, this will be divided by f, and if you take this in the right hand side, it will become positive, and you can write as u infinity by nu g prime by, you see here g square is there. So, you are dividing, so it will be g cube. Now, you can see in this equation we have separated the variables. Left hand side is function of eta only and right hand side is function of x only, and these are equal. So, obviously, it will be equal to some constant, right. So, you can write that equal to some constant k. Okay. So, it will be some constant k, okay, because it is function of eta only, okay, function of eta only left hand side, and this term is function of x only. Okay. So, obviously, because u infinity nu are constant for the flow over flat plate and g is function of x only. So, it will be equal to some constant k, and that we need to find. Now, if you see, so if you consider this term equal to k, then you can rearrange it as u infinity by nu g prime by g cube is equal to k. Okay. So, you can see you will be able to integrate it 1 by g cube, g prime is dg by dx is equal to k nu by u infinity. If you rearrange it again, so you can write dg by g cube is equal to k nu by u infinity into dx. So, now you can see that this equation now you will be able to integrate. So, if you integrate it, integrating the above equation, okay. So, you can see you can write minus half 1 by g square is equal to k nu by u infinity x plus some constant C 1. So, this integration constant C 1, what will be the value? Now, you see physically, if you see this figure, as x tends to 0, your boundary layer thickness delta tends to 0. So, you can see x tends to 0, okay, at the leading edge of the plate, your boundary layer thickness will be tending to 0. It is not actually 0, although we write that x equal to 0 is equal to delta is equal to 0, but at the edge, at the leading edge of the flat plate, delta will not be exactly 0. So, that is why we are writing x tends to 0, delta tends to 0, and delta is function of x, and we have seen that eta is of the order of y by delta, right. Eta, because we have already seen that the plot for the similar velocity, so it will be y by delta, okay, and that we have written eta is equal to y into g, because delta is function of x and g is function of x. So, you can see as x tends to 0, delta tends to 0, obviously at x tends to 0, g will be tending to infinity. That means 1 by g will be tending to 0. So, from here you can see that x tends to 0, 1 by g will be tending to 0. So, obviously, the integration constant C 1 will be 0. Okay. So, now if you see from here, you can write g square is equal to minus u infinity divided by twice k nu x. Okay. So, you can write g is equal to root minus u infinity divided by twice k nu into x. So, now you can see in this expression k is constant, right. So, for simple calculation we can take any value of k. So, let us take the value of k as minus half. So, that this minus will go away because minus minus will become positive and here 2 is there, and if you take half then this 2 will get cancelled and you will get a simple expression. Okay. So, let us take the value of k which is constant as minus half. Okay. So, if you put k is equal to minus half, then you will get g is equal to root u infinity by nu x. Okay. In some book you will find this eta as u infinity by 2 nu x. Okay. So, depending on how they have taken this constant, it will vary, but in our calculation we are assuming the constant as minus half. Okay. So, that we will have the simple expression. So, g now we can write as u infinity by root g, we can write now as root u infinity by nu x. So, now you can write eta is equal to y into g. So, you can see that it will be y into u infinity by nu x. Okay. So, this is the similarity variable. Now, we got the expression of g which is a function of x as root u infinity by nu x. Okay. So, that we have found. Now, let us take the other part. So, this part d of d eta f double prime by f, that is also equal to k, and now k we have already assumed minus half. So, this will be equal to minus half. So, let us write that. So, now you can write d of d eta f double prime by f prime divided by f is equal to k. Okay. And k already we have assumed as minus half, right, k is equal to minus half. So, k is equal to minus half. So, it will be minus half. So, if you see, it will be d of f double prime by f prime is equal to minus half f into d eta. So, you can see in this equation still f is unknown, okay, f is unknown, but f is function of eta. So, now let us take that you can integrate it. So, if you integrate this equation, then you will get integration f d eta, and now as f is unknown, okay, it will be difficult. So, let us assume or choose a new variable f as integration f d eta. Okay. So, we are choosing f is equal to integration f d eta such that your df by d eta will be f. So, you can see that we are choosing integration f d eta as a new variable f such that you will get df by d eta is equal to f. So, here you can see in this integration when we are writing it. So, obviously, in here this it includes the constant. So, that when we are integrating this, so obviously there will be integration constant, and if you take the derivative, so this constant will become 0. So, it will be df by d eta is equal to f. Okay. So, now we can see what is df by d eta. So, we have written f is equal to u by u infinity, right. So, df by d eta which you can represent as f prime as u by u infinity. Now, what is the physical significance of f? Okay, small f. So, we have chosen a new variable, okay, f. So, what is the physical significance of it? Okay, let us see. So, we have defined f is equal to integral f d eta such that df by d eta is equal to f. Okay. So, this f, okay, whatever f we are defining, this is the having the physical significance. So, f is equivalent to stream function. Okay, so, whatever new variable we have defined f, it is having the physical significance because it is equivalent to stream function. So, let us see. So, how do you define the velocity u? You define if you have psi is the stream function, okay, then how you define u? You define as del psi by del y. Okay. So, you define as a del psi by del y. Now, you can write d psi by d eta into del eta by del y, and del eta by del y is g. So, you can write d psi by d eta. Okay. And in earlier slide you can see we have seen that df by d eta is u by u infinity, df by d eta is equal to f is equal to u by u infinity. Okay. So, you can see this u you can write as u infinity df by d eta is equal to g d psi by d eta. So, that means you can write df by d eta is equal to g by u infinity d psi by d eta. Okay. So, you can see from this expression, okay, df by d eta is equal to g by u infinity d psi by d eta. So, you can see f is equivalent to stream function with a factor, okay, g by u infinity, but the physical significance of f is that it is equivalent to stream function. Okay. So, at the wall in the plate, okay, you can assume the value of f as any constant, because it is a, you can assume flat plate as a streamline, and along a streamline your stream function will be constant and any value you can take. So, for simplification we will take the value of stream function or f as 0 on the flat plate. So, now what we are getting from this expression? So, you can see now integration f d eta is f. So, you can write d of f double prime by f prime as minus half f d eta. So, if you integrate it, so you will get f double prime by f prime is equal to minus half integral f d eta such that it will be minus half f. Okay, and integration constant I have told that it is already included in the f. So, you can write is equal to minus half f. Okay. And from here you can see f we have defined as df by d eta. So, f is df by d eta. So, f prime will be d2f by d eta square. Okay. So, this will be f prime, it will be f double prime, and f double prime will be just d cube f by d eta cube, that means f triple prime. So, now if you put it here and rearrange, what you are going to get? F triple prime plus half f double prime, because f prime you are multiplying, is equal to 0, okay, which is known as Blasius equation. Okay. So, now you can see we started with the partial differential equations, because continuity equation and momentum equation which are boundary layer equations. So, those equations were partial differential equations. Using the similarity method we converted this partial differential equation to ordinary differential equation, because this you can see this is your ordinary differential equation, because they are ordinary derivative, right, df by d eta d2f by d eta square. So, this is ordinary derivative. So, you have converted PD to ODE using similarity method. Okay. Now, you see about this equation, ordinary differential equation. So, obviously, you can see it is a non-linear equation, because you have f double prime, and it is a third order ordinary differential equation, because you have f triple prime. So, you can see this is a third order non-linear ordinary differential equation. Okay. And here f is function of eta only, that is why it is ordinary derivative. Now, how to solve this equation? Okay. So, Blasius used a power series to solve this equation, but in this course we will not elaborate that, but you can use some numerical approach to solve this ordinary differential equation, because you know different numerical techniques, right. So, you can use Runge-Kutta method to solve this equation with some initial and boundary conditions. So, in this case obviously it is a boundary value problem. You can see from the boundary conditions which are known and which are not known. So, first let us write the boundary condition. Boundary conditions. Okay. So, obviously you see that at y is equal to 0 at the wall, okay, you have u is equal to 0 and psi is equal to constant. Okay. At y tends to infinity, that means y tends to delta, right. So, you have u tends to u infinity, because it will approach free stream velocity, and at x equal to tends to 0, where at the leading edge of the flat plate, here also your u tends to u infinity. Now, you convert the boundary condition in terms of f. Okay. So, at y is equal to 0, now you see what is the expression of eta. Okay. So, you see eta we have already written as y into u infinity by nu x, okay, and f is function of eta only. Now, you can see here. So, at y is equal to 0, obviously eta is equal to 0. So, at eta is equal to 0, okay. So, u is 0. So, u is 0 means you can see u, how we have defined f is equal to u by u infinity, okay, and f is nothing but f prime. So, from here you can see at eta is equal to 0, u is equal to 0, that means f prime is equal to 0, right. Now, if you see in terms of stream function, because we have already shown that f is equivalent to stream function. So, you can consider the flat plate as a streamline, and along a streamline stream function will be constant, and that constant value we can choose 0 for convenience. So, we can write f is equal to 0. Now, if you see these two equations, now at y tends to infinity, right, y delta means infinity, also you can write, means away from the wall. So, you can write at y tends to infinity or x tends to 0, in both the cases eta tends to infinity, right, because y tends to infinity, then eta will be tending to infinity, and x tends to 0, that also eta tends to infinity. So, what will be your value? So, you can see u tends to u infinity. So, that means f prime will become 1. Okay. So, f prime will be tending to 1. Okay. Now, you can see f prime will be tending to 1, okay, in this case. And what is the physical significance of f double prime? Okay. So, in the f double prime, so from here you can see, okay, so at eta tends to infinity, what will be the velocity gradient? So, at the edge of the boundary layer your and outside the boundary layer you have free stream velocity u infinity. So, obviously you can see the velocity gradient will be 0, and what will be the velocity gradient? You can see f double prime will represent the velocity gradient. Okay. So, f double prime also will be 0. Okay. So, at the edge of boundary layer and outside the boundary layer, you can see that f double prime will become 0, because velocity gradient will become 0. Okay. So, now you can see from these boundary condition we have converted the boundary condition in terms of f, okay, and eta. So, you can see eta is equal to 0, your stream function is 0, we have just assumed 0 value, f prime will be 0, and at eta tends to infinity f prime tends to 1, and velocity gradient. So, f double prime will represent the velocity gradient. So, f double prime will be 0. Now, you can see that this ordinary differential equation you can solve using some numerical technique. So, you can refer some book, you can use Runge-Kutta method to solve this ordinary differential equation with these conditions. So, you can see here your the value of f double prime at eta is equal to 0 is unknown. Okay. So, at eta is equal to 0, f double prime 0 is unknown. Okay. So, you solve such a way that you assume the value of f double prime 0 at eta is equal to 0, because to solve this equation you need it, and satisfy that at eta tends to infinity, infinity you cannot have. So, as far distance for eta high value, f double prime will become 0, because velocity gradient will become 0. So, you can see f prime, f values are known at eta is equal to 0, but at eta is equal to 0, f double prime is unknown. So, you assume the value of f double prime 0 and such a way that you satisfy f double prime at eta tends to infinity, means far away from the wall it will become 0. So, it is known as shooting technique, because you have to assume and check whether it is satisfying that condition or not. If it does not satisfy, you change the value of f double prime 0. So, in this way you solve these equations, you solve this ordinary differential equation using Runge-Kutta method and shooting technique, and satisfy f double prime at eta tends to infinity as 0, assuming the value of f double prime at eta is equal to 0. If you solve this, then you will get these values. You can see that if you assume f double prime value at eta is equal to 0 as 0.33206, then you can see at eta tends to infinity at a higher value it is becoming 0. Okay. So, this is the value eta. So, this will be u infinity, it will be u infinity. So, you can see this is the eta value. So, 0 is at wall, and as eta increases, that means you are going away from wall. So, and you can see the value of f is equivalent to stream function, df by d eta is u infinity. So, this is your u infinity, and d2f by d eta square, it is the velocity gradient. So, that you are assuming this value such that your at eta tends to infinity it will become 0. So, if you plot it, so you can see the plot here. Okay. So, this is the plot of f. So, we have assumed f is equal to 0. So, it is satisfying, and away from wall means eta at higher value, okay, it is increasing. F prime is the representation of the velocity. Okay. So, now you can see f prime. So, f prime at eta is equal to 0, it is 0, but at eta tends to infinity, obviously outside the boundary layer it will become constant value, right, 1. So, you can see this is almost 1. So, this is your u is equal to u infinity, right. So, that means u by infinity will become 1, and you can see around eta is equal to 5, it is becoming almost constant, because it is outside the boundary layer and it is maintaining the free stream velocity u infinity. And f double prime is the representation of velocity gradient. So, obviously you can see velocity gradient will be higher at the wall, because wall shear stress will be there, and as you go away from the wall your velocity gradient will decrease, and outside the boundary layer obviously it will become 0, and you can see you have higher value at eta is equal to 0. As eta increases, your velocity gradient decreases, and at the edge of the boundary layer almost it is becoming 0. So, you can see almost at eta is equal to 5, your velocity is becoming almost 99% of u infinity, and that will define the hydrodynamic boundary layer thickness. So, delta will define where u becomes almost 99% of u infinity. So, that you can see it is becoming 1 and velocity gradient also is becoming 0. So, you can tabulate it, you can solve this ordinary differential equation using Runge-Kutta method and plot this table as well as this figure. Now, from the solution, Blasius solution, at eta is equal to 5, your velocity is becoming almost 99% of u infinity. So, you can see from this table. So, at eta is equal to 5, you can see it is becoming almost 99% of the u infinity. So, let us find what is delta x. Find delta x. So, let us define delta as the distance from the plate where u by u infinity is 0.99. So, obviously, you can see, so around eta is equal to 5, it is becoming 99%. So, at y is equal to delta, obviously, it is becoming this. So, eta we know. So, at place of y you put delta u infinity by nu x. So, this is the expression of eta we are writing is equal to 5, and you can write delta is equal to 5 into nu x by u infinity, and if you rearrange it. So, you can see delta by x will be 5 by root r e x. So, now you can see from the Blasius solution we got the value of delta by x as 5 by root r e x, and if you recall that when we use scaling analysis we have shown that delta by x is order of 1 by root r e x. So, from scaling analysis delta by x is order of 1 by root r e x. So, now you can see that delta by x is order of 1 by root r e x, and you can see from the Blasius solution. In some book you can see that this value 5 whatever we have taken, it can be taken as 5.2 or 4.9, because from this table you can see this is also 0.99. So, in different books you can see that this value of eta is taken as 5.2 or 4.9 kind of thing, but we have chosen just 5. So, delta by x is 5 by root r e x. Now, let us find what is the wall shear stress, right. So, find wall shear stress, which is function of x. So, now tau w you can write mu del u by del y at y is equal to 0, right. At the wall y is equal to 0, we are finding tau w, and u by u infinity we know that it is f prime. So, you can see now you can write mu, so del u by del y. So, you can write u infinity del f prime by del y at y is equal to 0. Then you can write mu u infinity. Now, this you write in terms of eta derivative, right. So, you can write df by d eta into del eta by del y at eta is equal to 0. So, del eta by del y, so you can see eta we have y by root nu x by u infinity. So, del eta by del y will be just 1 by root nu x by u infinity. So, if you put these values, so you can see this will be mu u infinity 1 by root nu x by u infinity, and it will be f double prime at eta is equal to 0. So, this value f double prime, what is the physical significance of f double prime? We have shown that it is a velocity gradient, and velocity gradient now you know from the Blasius solution what is the value at eta is equal to 0. So, if you go back to this table, you can see this is the value of f double prime at eta is equal to 0. So, if you put this value here and rearrange, you will get 0.332006. I am not writing. So, it will be mu u infinity divided by root nu x by u infinity. Okay. So, this is your wall shear stress. Now, let us write local skin friction coefficient. Local skin friction coefficient. Okay. So, this you can define as Cf is equal to tau w by half rho infinity square. Okay. So, if you put that, you will get 0.664 mu by rho infinity root u infinity by nu x, and if you rearrange it, you will get Cf as 0.664 by root r e x. So, if you remember that using scaling analysis also we have found Cf is order of 1 by root r e x. So, from scale analysis already we have shown that Cf is order of 1 by root r e x. Okay. Now, let us find what is the total friction force per unit width. Okay. So, total friction force per unit width of the plate. Okay. So, if you can integrate tau w dx from 0 to L, because this is the length of the plate. So, if you do it, you will get 0.664 rho u infinity square nu L by u infinity. Now, average skin friction coefficient, now you can write average skin friction coefficient Cf bar will be f by half rho infinity square into area. So, that is L into 1. So, L is equal to 1.328 divided by root r e L. So, in today's class we have seen that we have started with the boundary layer equation for flow over flat plate. We used similarity method proposed by Blasius, and we converted the partial differential equations to ordinary differential equation using similarity method. So, similarity variable we have used as eta, which is function of two independent variables x and y, and we have used u by infinity as capital F, which is function of eta only, and we have converted these boundary layer equations to Blasius equation, which is your third order nonlinear ordinary differential equation. Then we have written down the boundary conditions, and you know that the value of f double prime, small f double prime, which is the representation of velocity gradient, is unknown at the wall. So, using some numerical technique like Runge-Kutta method and shooting technique, you can assume the value of f double prime at eta is equal to 0 and satisfy that f double prime at eta tends to infinity will become 0, because at the near to the edge of the boundary layer and outside the boundary layer your velocity gradient will become 0 for flow over flat plate. Then we have tabulated the values of f double prime with eta, and we have also shown the plot of f prime and f double prime, where f is the representation of stream function, f prime is representation of the velocity, and f double prime is the representation of velocity gradient. Then we have found the hydrodynamic boundary layer thickness delta from the Blasius solution, and we have shown that delta by x is equal to 5 by root r e x, and also we have found the wall shear stress, and from wall shear stress we have found the local skin friction coefficient and average skin friction coefficient.